Welcome everyone to the tutorial at CAV 2020 given by Professor Sriram Sankaranarayanan. It is my great pleasure to welcome Sriram Sankaranarayanan for this tutorial. So Sriram is a very distinguished person. He's an associate professor at the University of Colorado at Boulder. And his research interests are pretty much everything that the CAV community cares about, starting from cyber-physical systems, program verification, machine learning, to name a few. Sriram obtained his PhD from Stanford University, working with Zohar Manna and Henny Sitma. He worked at NEC laboratories for a few years, and he's been at Colorado Boulder since. He has been a recipient of many awards, including President's Gold Medal from IIT Kharagpur, Siebel Scholarship, NSF Career Awards, and many distinguished paper awards. I know personally Sriram from our undergraduate days, where Sriram was a junior of mine, and we even shared the same hostel or fraternity. So it's a great pleasure to have Sriram give this invited tutorial for CAV. So welcome, Sriram. So thanks for joining. So most of the questions, the logistics, the questions will be on the Slack channel. I hope all of you have registered. The Slack channel for this tutorial is called Tutorial on Probabilistic something. So post your questions there, and I'm going to monitor for questions, and I'm going to post them to Sriram at appropriate time. And that's it. And we'll take a break somewhere around 45-50 minutes for 5 minutes, just for Sriram to get recharged. And we'll keep going after that. So welcome, everybody. Thanks for joining. Sriram, take over.
Okay, I hope you can hear me, and I hope you can see my screen. I will let Shuvendu do the talking for all of you. So please post on Slack, and I will have plenty of breaks to solicit and answer questions. Part of the tutorial is it's not a rapid cram session. It's more of a relaxed environment to explore ideas in probabilistic programming. And in this lecture, or in this tutorial, I'm going to focus mainly on the CAV community and what I personally think the CAV community needs to know about probabilistic programming. I was given a little bit of questioning about the choice of the title, Verificationist, which to some people sounded like a cult. Well, I considered the term verifiers, but verifiers are the things that we produce as programs. So it didn't seem to call ourselves verifiers. After all, furniture makers don't call themselves furnitures. How about verificationistas? Well, it's like fashionistas or baristas. Or CAV people. That sounds a little primitive. So in keeping with the theme of this talk, I tossed a coin and came up with verificationists. So there you go. That's the answer, a long answer to that question. So now to something more serious. What is probabilistic programming? Well, the tagline is probabilistic programming is a means for specification and inference for probabilistic models. So what are probabilistic models? Well, it's a form of machine learning, and fundamentally what it is you are given some data, and you would like to explain away this data. And the way we explain data is by coming up with a model. And the model says, how does the independent variable X give rise to the dependent variable Y? And you can have hypotheses. One hypothesis for this data would be that there is a straight line relationship between X and Y with some noise, and the data just comes from the straight line with some noise. Another hypothesis could be a different straight line with a different noise pattern. A third hypothesis could be a curve, a polynomial curve or a spline curve or what you will. Okay. Now you have a space of hypotheses, and you would like to choose hypotheses to explain data. So what does a probabilistic model need to do then? A probabilistic model in the best case needs to be completely self-contained. It needs to say, let's define a space of hypotheses that explain the data. All right, tell me all the hypotheses you would like to consider: straight line 1, straight line 2, straight line 3, curve 1, curve 2, curve 3. Or you could be succinct and say, all possible straight lines, all possible polynomials of degree 2. Okay, but that's not sufficient. You need to tell me a way to say which hypotheses do you prefer against which other hypotheses. After all, you could have infinitely many hypotheses that do, if you don't have a preference, then there are infinitely many incompatible hypotheses that could be equally good or equally bad. And last but not least, you need a way to say what's the likelihood that if H1 were the true hypothesis, I would actually see this data. All right. So this is very important for machine learning. You need to specify all of this either implicitly or explicitly. So probabilistic programming is a way by which you can think of programs as specifying models. And the program itself contains all of this information that you need to solve a machine learning problem of this form. All right, that's fundamentally how one should think about probabilistic programming, coming from statistics and coming from machine learning, which is where this whole field comes from. All right. So let me give you a more concrete example of this process in action. And for that, I picked on some colleagues of mine who are gracious enough to let me do that. Saeed Tispas-Niari is a PhD student who's finishing up and joining University of Texas, El Paso in this fall. Pawel Cherney and Ashutosh Trivedi, you know. So they had a paper last year in CAV 2019. Well, in CAV 2019, their paper was about timing leak analysis or timing side channel analysis. And there they looked at a social network example. In the social network, a user can select whether to enhance their image, and this is secretly enhance their image. After all, when I post a picture,
sorry.
Okay.
Sorry to interrupt, Sriram. It seems that there's some issue with the live stream. I'm gonna just take like a couple of minutes, if you don't mind pausing.
No problem. I'll pause.
Yes,
people can collect your thoughts and ask me questions while
yes,
while we do that.
So give me a couple of minutes, and
No problem.
in case you miss something important.
Yeah, will do. All right. So let me just start off this slide again. Okay. So as I mentioned, this is a concrete example of this whole process of probabilistic programming to illustrate how it all arises. And so this is taken from a CAV paper last year by Saeed Tispas-Niari, Pawel Cherney, and Ashutosh Trivedi. The title of the paper is on timing leaks, or looking at timing side channels. And they were looking at a social network example where the social network user can say, secretly apply some filters to enhance their image, or just serve their profile without any image enhancement. And for some reason, this image enhancement is done every time someone tries to download the profile of a user. And they did some experiments on this network where they looked at the size of the profile against the response time from the server or the social network. And you can see there are two kinds of points. There are red points where these corresponds to users who have enhanced their image, and green points, and these corresponds to users who have not enhanced their image. The purpose of their paper was deeper than what I'm going to say. They were talking about entropy, and they were talking about timing side channels. A lot of it is also being covered in the other tutorial. But here, one of the things they did was they used clustering, and they tried to fit a model to explain away these two categories. And they said, okay, so let's try and fit a single straight line through the red points and a single straight line through the green points after figuring out which points are likely red and which points are likely green. And A1 and A2 are the slopes of these two straight lines, and B1 and B2 are the intercepts of these two straight lines. And the goal here is to predict, given a query point, let's say, whether the query point belongs to the red class, or this user has enhanced their image, or it belongs to the green class, whether the user has not enhanced their image. And so one of the things to note here is that this kind of a machine learning procedure ends up providing selecting a single hypothesis from the given set of all hypotheses. Okay, let me come up with a different way how you would do it using a probabilistic program, and that would be like a dip in the deep end of the probabilistic programming pool. And this is how it looks like. So in probabilistic programming, we will think like making up a generative model. And I'm going to use the kind of notation you would see commonly in statistics, and this is somewhat like a hierarchical Bayesian model. Okay, I will explain what that is in a little bit more detail as we progress in today's tutorial, but let me try and explain what this means. So the idea behind a generative model is a story. It tells a story of how data like this could have come about, not this specific data set, but abstractly any data set of this form. How do you think that data set got generated? And if you think about it, we can say, let us draw two uniform random numbers in this range between 0.01 and 100, and let's call them A1 and A2. And secretly, these are going to be the slopes of the two straight lines that I'm going to fit through the two categories 1 and 2, 1 standing for green, 2 standing for red. Let's say B1 and B2 is the intercept, and let's draw a uniform random number between 0 and 5. Okay, let's draw another uniform random number called P between 0 and 1, and this P is going to represent the proportion. So what proportion of the data refers to green versus what proportion refers to red, and this P is going to be a proportion. Okay, and these numbers, these distributions are called prior distributions. They would actually be more like a hyperprior, but I will not get into all of that details. There are books that go into that detail. All right, and now you have J ranging from 1 to n, which is the index for the data. So you have n users, n data points, and you select a category for each user, and you select it like this. You select a category of green or 1 with probability P, or 2 with probability 1 minus P. All right, and now you have selected a category for each user, and you say the Y for that user is the slope times the X for the user plus the intercept plus some noise. And this is something like a measurement noise. No measurement is free of noise, so you have some measurement noise. Okay, and so this is a generative model. And there is nothing specific in the generative model to this data, to this example. It tries to generate all possible pairs of two straight lines with all possible divisions of two categories. And there are infinitely many possible ones. But what you next do is you serve up some data. And we are going to use this process of Bayesian inference to condition this generative model. And this process will be called conditioning. We're going to condition this generative model on this data. And after you condition, you get something called a posterior. And I'll talk about that in more detail using much simpler examples. But here is the high level picture, right? Using that, you can now talk about what's the probability that of the category variable for the query point given the X and Y for the query point. Okay, and this is the last bit of the inference where you answer a question that you care to answer about. And this is how probabilistic programming, or the Bayesian approach to machine learning, is going to work at a very high level. All right. So let me pause here maybe 2 minutes and answer some questions if people have any questions so far.
Sriram, these are probably questions a few slides back,
Okay.
but there is one question that says, are these hypotheses an input to the program, or they part of the ML program? And I believe this goes back to your previous slide, or perhaps the start of this slide.
Absolutely. That's a really good question. Are the hypotheses somehow in the background unspecified, or are they part of the program? Well, that's where the implicit versus explicitly stating the hypothesis is going to come in. Here in probabilistic programming, these hypotheses are explicitly stated through the generative model. And there are ways by which you can have implicit hypotheses. So you can say that, you know, my hypothesis is a Gaussian process, and or my hypothesis is a polynomial model, or it's a neural network. So there are different styles of machine learning where your hypothesis space is implicitly stated just because you're going to use machine learning, or you're going to use SVM with polynomial kernels. But that's a different world. Here, the hypotheses are going to be part of the program, at least in this style I'm presenting. The hypotheses will be part of this program. I will show you in a second. But here, if you think about it, your hypothesis space is here. In this example, your entire hypothesis space is all possible values of A1, A2, B1, B2, P, category J, Yj, Xj. That's your, or xj, and yj is what you want out of it. But you can see how your hypothesis has been encoded here in this generative model. Is that good?
I hope so.
All right. Well, if it's not good, we'll continue on this, right?
Yeah, there's a related question. You can feel free to take it later. Is in ML, the algorithms try to find some kind of best hypothesis. How is probabilistic programming different from such algorithms?
Aha. Hold on to your question. We are going to answer that. All right. So it is and it isn't different. So we'll talk about it. What is great about probabilistic programming that's different from classic ML? All right. And if you see, I will hopefully give you that sense as I go through this. If I don't, this is something we should definitely talk about. Great. So what's a probabilistic program then? Well, it's a programming language equipped with some extra things. And please don't try to read this program. My students complained about this program and I gave this practice talk and they said, this is intimidating when you put a program like this. I agree. This is a program written in some kind of OCaml. It could be any language of your choice, literally, but it's a program where I have put some samples and flips. And what I'm trying to do is I'm trying to express this model from the previous slide in a program. And what the program has done is it has defined a space of hypotheses. Oops, didn't mean to do that. It has defined a space of hypotheses. It has defined a generative model of how X gives rise to a category and Y. It has in it the data as some kind of conditioning statement, and it has in it the query. Everything that was said in the generative model of the previous slide is exactly what is being said in this program in the syntax and using the semantics of some of these programming language constructs with some extra funny statements shown in red. And this is what probabilistic program is going to do for you. It's going to have all of this packaged up in a program, and we are going to run inference on this program. You can't run this program in the normal way, but you can run a special inference procedure on top of your interpreter, and somehow that's going to do the inference. And if you did that, what will happen is I took some data points here in blue instead of green and red. And you can see how the posterior is going to look like. So what the probabilistic program does here is it generates a lot of hypotheses. It generates a lot of straight lines, not a single straight line, each of which has its probability, and that's going to be called the posterior probability. So rather than look at a single hypothesis, it's still going to give you a space of infinitely many hypotheses, but it's going to have the posterior distribution of the hypotheses. So which means that they are now conditioned to the data that you have. Originally, all possible slopes were allowed. All possible intercepts were allowed, at least all practically meaningful slopes and intercepts were allowed in a very wide range. But having conditioned with the data, you see that it's narrowed down considerably the set of hypotheses, but you still have a set of hypotheses. And now if I give you a query point, some kind of a query point that lies here, I should have plotted that, then your probabilistic programming says, well, it's red with 97% probability and blue with 3% probability. So this is the answer, like a partial answer, which we will keep giving to this question. Does probabilistic programming give you a single point hypothesis, or does it give you a distribution over the posterior hypothesis? Well, in its true form, Bayesian inference gives you the distribution, the full posterior distribution. So you don't get one hypothesis, you get all possible hypotheses after you've conditioned it on the data. And that's called the posterior hypothesis or the posterior distribution. And different hypotheses have different weights. So as you can see, there is a kind of thickness. If your lines here have more thickness, then they have more weight in the posterior, and then certain lines have less weight, or thinner lines have less weight in the posterior. So you can see that. And instead of predicting whether a particular point is definitely red or definitely blue, this kind of inference gives you a probability. It says, you know, I think it's red with 97% probability, and I think it's blue with 3% probability. So this is essentially a big difference between probabilistic programming in the Bayesian sense, where you get a bunch of hypotheses, versus trying to find a single hypothesis, which is also something probabilistic programs can do. But that's something I will talk about in a second. I'll define this better in a second, and I'll give you more examples, simpler examples, where we can actually get into what the examples are doing. Okay, so let me run on to one more slide and then take some more questions. All right, so what's a probabilistic program then? Well, you can think about it as a programming language where we are given the ability to sample from probability distributions. This is not new. All programming languages that we program in that are reasonably general purpose have random number generators. You can get uniform random numbers, and you can shape your distribution of random numbers if you know how to do that. And then you can get Gaussian random numbers and exponential random numbers and all of that. So you have the capability of generating random numbers, sampling from distributions. The important thing about probabilistic programming, it also provides you a way of conditioning the program using observations or observe statements. So your program has sample statements. I will talk about flip. Flip is a special kind of sample statement, okay? And I'll talk about other kinds of sample statements. You can sample from Gaussians, you can sample from uniform, and you can make observations on the variables of the program. So you can say, I observe at this point that X is 14.5. So roughly, what does a program like this mean? So a program like this, you can think about executing this program. So when you execute this program, let's start with sampling from a uniform random number. Let's think about two executions, orange execution, a green execution. In the orange execution, let's say we generated P equals 0.62. In the green execution, let's say we generated P equals 0.8. All right. Now I get to a flip statement. So flip of P tosses a coin whose probability of turning up heads or true is P. So here I toss a coin and it gives me true with probability 0.62. But in this example, it gave me false. Well, here I would have gotten true with probability 0.8 in the green example, but it gave me false again. Fine, such is life. I move on. So then when I'm in false, I get to the else part of this branch. Then I sample a Gaussian. Here the Gaussian is centered at 14 with standard deviation 0.5. And I call the result X. So here I get X equals 11.5. And let's say I am supremely lucky somehow. Okay, so lucky that you can't imagine how lucky. And let's say I got 14.5 and 11.5. All right. In the execution with 11.5, when I encounter this observe statement here, my execution doesn't proceed because observe X 14.5 says X has to be 14.5. Think of it as an assertion. All right. It doesn't proceed. Whereas in this other example, it proceeds and then the entire program returns the value of P, which is 0.8. So in probabilistic programming, you have sampling and you have conditioning. Conditioning can either block executions, or we'll look at other forms of conditioning that can weight up or weight down the probability of executions. All right. So roughly, this is how probabilistic programs will work. There are going to be sample statements. There are going to be conditioning statements, and we are going to work with that. All right. Maybe I can take a question or two right now, if there are.
Okay, yeah, there are some questions, Sriram. So I must mention the initial questions I should have mentioned. They were from Shyam and Saptarshi.
Okay.
And now there's a question from Marcel,
okay,
who's saying, are there hypotheses or functions not expressible with probabilistic programs?
Well, that's a really good question. Yes, of course, right? I mean, you are working in this Turing complete world, right? Your whatever functions can be expressed in your programming language formalism are the functions you will express as part of your hypothesis space. So, which means any Turing complete, class of functions are things that you can express. And this is a topic that people have kind of explored in some surprising amount of depth. And I can give you more references, but there is this whole notion of universal probabilistic programming by Frank Wood. If you look at his lectures, his tutorials, he talks about exactly this point. But Turing complete is fairly good. But there are some probabilistic programming languages that are not Turing complete. So you will not get this full generality. There are going to be big restrictions on what kinds of hypotheses you can express. But certainly, if you have a programming language and you're allowed to write arbitrary programs with some, restrictions maybe, or without any restrictions, it depends. you can get up to Turing complete, right?
So I'm going to slide in one of my questions before there's another audience question. So
Sure.
I always thought of these observe as assumes as opposed to assert, because assert fails the programs, assumes blocks the execution.
Yes,
is that similar to? Okay, good. So then we have.
Go ahead.
Then we have another question from Augustine, who says, is the conditioning of programs given observations similar to what is called training in ML? Slide 7.
Absolutely. It is training, right? But it's a different style of ML. This is more of the Bayesian style of ML. And in this style of ML, this is exactly what training is. Okay, and I will explain how this is training in a second. But this is exactly it. This is training, and we look at different kinds of conditioning. This kind of conditioning is very brutal. Stop the execution if X is 14, not 14.5. If you ran this program, you will have to be extremely lucky, like measure 0 lucky, to get this program to give you any value in real life. So obviously, this is called hard conditioning, but there are other forms. But this is exactly what training would look like.
Do you want to take a few more questions or keep going?
I'll take a few more questions. It's
okay.
perfectly fine. I can always skip when I talk about other people's work. Hopefully
okay, so there is a question from Ganai who's saying, can we have declarative statements in the probabilistic programming? How generation model works with relation variables?
Can we have, sorry, what kind of statements?
Declarative statements.
Yes.
And
yes, absolutely. There are probabilistic programming languages that are based on data log or Prolog or logic programming. By the way, hi Malay, if it's Malay. Yes, yes, there are, and you can do that. It works exactly. You can have joint distributions, right? I mean, probability distributions are inherently declarative in a sense. I can say, instead of saying X is an input, Y is an output, you can simply have a joint probability between X and Y, and that's your relation, right? And if you talk to a category theorist, they will immediately say this is like a Jiri monad, and there is a lot of work on that too. But yes, a lot of this tends to be declarative. And that's very, very important. There are lots of probabilistic programming languages that have come from the Prolog data log world as well.
Okay, well, there's one more question and then move on. What would a symbolic variable look like in a probabilistic PL?
What is a symbolic variable?
I do not know.
Okay, well, we'll talk about this. I will talk a little bit about symbolic versus sampling-based approaches. Right now, you're basically thinking when I sample P from a uniform distribution, that should give rise to a number, right? And it depends on how you want to run your program. What we'll have to do is somehow we have to redefine how these programs have to be run. Otherwise, it's not going to work. And we'll talk about that. And there are some symbolic approaches. I do have something to say about that. All right, I will move on just to get through to some semantics before I stop because we are already running late. But these are great questions. Please keep them coming. I will adjust the length of my talk based on interest and questions. I'll post whatever I couldn't get to. I'll post it on YouTube. Send out an email. All right, we'll work with that. So, what is probabilistic programming at the end of the day? Well, these are going to be models. Another way to think about it. Now, I've given you three ways to think about it. They are all related. They are all the same, but they are different ways people think about this. The third way is a probabilistic program is a model of a probability distribution. At the end of the day, a program like this, you will see, will specify a distribution like this. Okay, using sampling and conditioning, you're somehow defining a distribution, and this is going to be the distribution that comes out as a result of running this program. In this case, I've run the program using my own probabilistic programming inference engine that I built for my own fun. And it gave rise to a histogram plot of this distribution. There are different ways of accessing this distribution. We'll talk about it. But one thing you should take away from this, the meaning of a probabilistic program is going to be a distribution. It's a way of constructing distributions. Think of it as a calculus for building distributions using sampling and conditioning. You wouldn't go wrong. All three are equivalent in a way. And how are they equivalent? Will come about through Bayesian inference. All right. So what about running a probabilistic program? Well, there are going to be multiple ways of running a probabilistic program. You can do exact inference, and there are some people who are doing it. I will mention their work. And in exact inference, when you run a program, it takes a lot of time. It communicates with some solvers like your awesome Mathematica and Maple and some inbuilt solvers and all that. And it comes up with a symbolic expression like this. This is not exactly correct. I have rounded down floating point numbers, which I shouldn't be doing, but I'm human after all, so it has to fit in the slide. So I put a number thing like this. So this program is actually this distribution. We can explain why, and it's a nice exercise to convince yourself it is this distribution. Or you can do sampling-based inference, which means that you apply some Monte Carlo method. And when you apply this Monte Carlo method, somehow it guarantees that after running lots and lots of samples, you get this same distribution here. Okay, so that's another way of thinking about it. And a third way of thinking about it is through point estimates, which means that you get a single point estimate from this program. You get an expectation of the return value of the program. You get a moment of the return value of the program, or you get something called the maximum a posteriori, which is like a single point which has the maximum density. And this is where a lot of machine learning approaches like TensorFlow come in, because they, in general, without any extra effort on top, will get you the maximum a posteriori of this distribution somehow. All right, so a lot of machine learning is based on point estimates or single points. Here it's based on a map estimate. There might be a typo here. I'll just put a question mark. This might have been 1 minus p, I think, but I apologize for the typo, but it's a good place to, if you want to think about it later on, I'll post my slides, try and work this out. It's a good place to do so. But these are 3 different ways you're going to interpret a probabilistic program. So this is another partial answer to a great question that was asked right at the beginning. Do probabilistic programs give you a single value, or do they give you lots of values, or what? Well, ideally they give you a distribution. Well, you're not going to get a distribution in all cases because that's going to be very, very complicated and difficult. So they're going to give you samples from that distribution, which converge in expectation as the number of samples goes to infinity. Or you can get point estimates on the distribution. You can access the expectations, the moments, the map estimates, and so on and so forth. Different ways of getting point estimates. Hopefully this is good. Let me.
There was a quick question. Sorry to interrupt. There was a question about the axis from Stavros. What was the axis on the slide? The two X and Y axis. It was hard to read.
X axis is the return value of the program P. Y axis is the density. Okay. And I think this is correct because look at this program. So let me go into this program. Okay, it samples a uniform number between 0 and 1. It flips a coin and it says if this P, whatever I sampled, I flip a coin with that probability. If it comes out true, I sample from a Gaussian. So this is a Gaussian which is centered at 10, or I sample from a Gaussian which is centered at 14. All right. And then I observe that X is 14.5. So what happens here is I am going to be, the way to get 14.5 is more likely, much more likely if I sample from this Gaussian here. All right. So it's going to be then, it's much more likely that this flip gives rise to false. I'm just qualitatively explaining how this program is going to work, which is much more likely that this P is going to go towards 0. All right. So this is how the distribution will look like. This form 1.99 times, I think it should be 1 minus P plus something is going to be a different way of expressing the same distribution, for which I have to do some symbolic derivation, which I'm not going to do. But to answer Stavros' question in a fewer words, P is the return value of this program because the program returns P at the end of the entire thing. And this is going to be on the x-axis. The y-axis is the density. Hopefully that's good. All right. I will keep moving. And Stavros, if you have follow-ups, please feel free to ask. Can I keep moving, Shuvendu? All right, will do. Okay, so throughout this program, I'm going to use an ML-like language. I Having taught PL a lot of times, this is the language in which my students in my undergrad PL class do their toy interpreter, and they encode all of these things. And I really like languages like this with semantics, without having to talk about side effects, without having to talk about arrays and stores and so on. That doesn't mean that all probabilistic programming languages are functional. Functional is a really good choice. Being declarative is a really good choice for probabilistic programming without having to worry about side effects and such. So I hope everyone is familiar with let bindings. These are just your assignment statements, except these are going to be like const. You're not going to allow mutations. You can have distribution as types or values in your program. You can sample from them. You can have your regular if then else statements. When I say let rec, that's a recursive definition. So I'm allowing things on the left and right. I can declare functions. You have your standard observe statements. And you remember the entire expression, I have this semicolon, which is your composition operator, which means that this entire bracket evaluates to the value of y after running observe. But I should say observe has a side effect in your program, which should be clear when I talk further about this. But this is the language I'm going to use. Let me talk about flip. Flip is just a sample statement from a Bernoulli distribution with the probability of turning heads as p. Choose is another kind of a statement where if you give me a list, I just sample with equal probability one of the values of the list. In this case, there are 4 values, so I sample with 1/4 probability. Okay, I hope this is clear. Not too much. Whenever I come up with a program I have to explain, I will explain in detail, and you can always stop and ask questions. And Shuvendu, you can interrupt me. I think that's working out just fine. I will go on for 5 more minutes, try to get you through the initial part of this tutorial so that at least we can, before the break, we can have some more of an understanding of what probabilistic programming semantics is. Okay, I mentioned conditioning. There are 2 forms of conditioning, hard conditioning and soft conditioning. So hard conditioning is essentially going to be like an assume statement, as Shuvendu pointed out. You are going to write a Boolean condition involving some program variables, and if the condition passes your program state, your execution just continues as if nothing happened. But if your condition is violated, your execution stops, and that's as if your execution never happened. All right, it's like nothing happened. That kind of execution did not happen. You just ignore it. All right. So this is how condition works. All right. So you can have this observe statement, which is a funny statement here. I observe x to be exactly 10. It's the same as this condition statement, x equals 10. They are the same thing. All right. You can have different kind of conditioning, which are going to be called soft conditioning. So in soft conditioning, what will happen is you are allowed to condition a program variable, let's say x, and let's say x has the value 12.5. You're allowed to condition this program variable with a Gaussian centered around 15 and 0.5. What does this mean? This means something like this. I have a Gaussian which is centered at 15. It has a standard deviation of 0.5, and I am observing x is 12.5. So what is the likelihood, or what is the density function of observing 12.5 when you're given a Gaussian distribution? Well, it's going to be, I don't know, 5 standard deviations away, if my mathematical skills are still what they used to be 10 minutes ago. Yes, 5 standard deviations away. So let's say this is like the likelihood of this observation is 10 to the minus 5, something like that. Sorry, my Gaussian distribution knowledge is not good. I need a calculator, but let's say it's 10 to the minus 5. So what it means is that I pass this observation with this probability 10 to the minus 5. But this never blocks. This kind of soft conditioning never blocks. The execution keeps proceeding. What just happens is it became a lot improbable because I'm observing a value 12.5 under a Gaussian of 15 and 0.5. Another kind of soft conditioning is I can observe some condition 9.1 less than equal to x under a Bernoulli distribution. What this means is if x was like 8.4, which means it passes this condition, then I proceed and I say the probability of proceeding is 0.95. On the other hand, if it were, let's say 10.2, then I proceed, but I proceed with a probability of 0.05. And I just augment the probability of the path that I'm going to be executing with these numbers. All right, and I will get to that in a second. But there is soft conditioning, and this is much more nicer. You don't block any execution. The execution just proceeds as if the probability kind of just went up and down. So I'll stop here for a few questions if there are any.
I think we can keep going, Sriram. So we covered most of it. Let's see, there's one question which is on slide 10. Is the symbolic description of posterior a probability density function?
It is going to be. So there is going to be a split here between continuous and discrete probabilities. It's going to be a density function for continuous probabilities. Programs with discrete probabilities, it's actually going to be more of an actual value. And there, the semantics of probabilistic program gets into a little bit of trouble, which I will try to explain, but it's a huge story there. But I'll try and explain how you get two different types of semantics, if you will, one for programs with continuous distributions, another for programs with discrete distributions. You can unify them, but you need a lot of measure theory to do that. Okay. So let me, I think the questions have slowed me down enough, and many of these questions have been anticipatory. So I'm going to go through some parts of this in a little bit more, with a little bit more speed, and maybe we can go for 10 more minutes and have a break. Is that okay, Shuvendu?
Sounds good.
All right. Okay, so let me talk briefly about Bayesian inference and get to the meaning of probabilistic programs, which is a big topic, but we'll get to it quickly. And there is a nice analogy here called the Garden of Forking Paths from this great book called Statistical Rethinking, where it's explained very nicely in this way. Okay, so it all began back in the 17th, 18th, and 19th centuries. And here is a very nice question at the very beginning of Bayesian inference, which was asked by Pierre-Simon Laplace, who said, will the sun rise tomorrow? Or in probability terms, he wanted to answer a question like this. What's the probability that the sun will rise at the n+1th day, given that the sun has risen consecutively for n consecutive days? And the way you want to think about problems like this is, let's go back to a coin with probability theta of showing up heads. And we would like to estimate this probability theta. And the way you do that, you run an experiment, you toss the coin 10 times, and you get 5 heads out of these 10 tosses. So how do you think about theta? Well, there are two approaches to thinking about theta at a very, very high level without going into a lot of ifs and buts. Theta is a real number. One approach says, well, theta is a real number between 0 and 1. It has a definite value. It's unknown to us. That value is unknown to us, but it's a real number. So what you can do in this approach is you can say, what's the most likely value of theta that explains this observation? And you can say most likely value of theta is 0.5. All right. And then you can say, what is the likelihood that theta was actually 0.4 and I saw this kind of a result, and so on and so forth. So you can do that kind of an approach, but you always insist that theta is a real number. It's a question of types, and you say theta is a real number. The other approach, which we are going to adopt throughout this talk, is the Bayesian approach, where you say theta itself has a probability distribution. Well, some people don't like calling it probability distribution, but let's just call it that. And let's say it has a distribution, and this distribution, let's say, models something like a prior belief. This has been debated a lot, whether it's a true belief, it's a subjective thing, or there is something more objective about it. Let's just say it's a prior belief about theta. So I can say, I have some belief about what theta is, and I encode it as a probability distribution. So it's not a number, it's a distribution, and the distribution somehow models my ignorance about theta or my uncertainty about theta. And in Bayesian inference, you're going to update the distribution of theta based on the outcome of an experiment. So what's the idea here? So in Bayesian, here is an example of a prior. So you can say, in my prior, and this is my prior, and you can say, well, theta can only take on 3 values, either 0.4 or 0.5 or 0.6, but no other value. And I believe that each of these values has 0.333 or 1/3 probability. And this is a way of specifying a prior. This is my prior belief. I believe that each of these values is equally likely. Okay, and then you apply Bayes' theorem. And this is the fundamental theorem in Bayesian statistics. It's also true for probabilities, but what it says is the probability of theta conditioned on n, and by n, I am just talking about this experiment. I tossed the coin 10 times, I saw 5 heads, is nothing but the probability of data given theta. So it's the probability that I would have seen n given theta times the prior probability of theta divided by P of n, and this is called something called the evidence. It's the normalizing factor in the denominator. This denominator is there to make everything add up to 1. Okay, and in the Bayesian world, this has a name. This is called the posterior probability. So in other words, prior probability meets the evidence, and as a result of the evidence, you get through the Bayes' theorem a posterior probability. All right, and what does the posterior probabilities look like here? Well, this is a simple calculation. For example, if theta was 0.4, then you can say, what's the probability of n given theta? So what's the probability that I have 10 tosses, I show 5 heads? I would have picked on Shuvendu, but I don't have the time to do that. So I will do it myself. So 10 choose 5 times 0.4, which is the probability of showing up heads to the power 5, times 0.6 to the power 5. Hopefully I got that right. Okay, times what is the probability of the prior? Well, that's 1 by 3. So this is probability P theta. The denominator I can estimate later. So I do this for 0.4, I do this for 0.5, I do this for 0.6. I normalize the whole thing, make it divide by 1. That's actually this P of n. When the dust has settled and my calculations have settled, I find that the probability of 0.4 and 0.6 in the posterior is 0.31, whereas the probability of having half has gone up to 0.38. All right, so this is essentially the prior has met the data, and after you have conditioned the prior on the data, you now have a posterior where one of the probabilities has gone up and the other 2 probabilities have come down. Okay, so this is kind of very, very important. What about different priors? Well, you can have, why go with the prior that I gave? It's a funny prior. You can have this prior called the uniform prior, which says, I have no knowledge about what the coin is. It came from someone I do not trust. They might have done something to the coin. So the probability of turning up heads is anywhere between 0 and 1. That's a prior. And when you take that prior and you apply to the Bayes rule, this is a form of Bayes rule which is very nice because you just write it as a proportionality constant and the denominator can come later. And this is very nice. And then you show that the posterior here is beta 6,6. It's a beta distribution. It's a kind of distribution with parameter 6,6. And as you can see, surprisingly, not surprisingly, the posterior peaks at 0.5. Okay, and this is called the MAP estimate, maximum a posteriori estimate, which is 0.5. But you have a distribution of theta, and this is the posterior distribution, the distribution after you have seen the data. You can have more funny priors, and this is called a spike and slab prior. And this prior says, well, I have a 0.4 probability of this coin being a fair coin. After all, how it's very difficult to have a biased coin that passes my eagle-eye scrutiny. So I will say 0.4 for fair, and with remaining 0.6 probability, it can be uniform. And this is called a spike and slab prior. It's a very strange mix of a discrete and a continuous distribution. Well, you can apply Bayes' rule, and you get a mixture of a beta kind of a distribution with a spike. All right, so before we take a break, let me just give 2 more thoughts here. First is, this whole process can be written as a probabilistic program. Here is how you write a spike and slab prior. Just like I said, let P be, if I flip a coin with 0.4 probability, then half. Otherwise, it's a sample from a uniform number between 0 and 1. This is my primitive way of rewriting a recursive function that tosses the coin n times and counts the number of heads. Basically, if n is less than 0, then 0. Otherwise, convert 1 flip of a coin to an integer and add it to the result from n minus 1 trial. So this just simulate n trials of a coin with probability p of showing heads. And then I observe that 100 trials of this coin yields a 54, 100 tosses yields 54 heads. And that's, I write it as a hard conditioning, as an observed statement. And the return value of the program is just P. So this is how I would write this as a probabilistic program. What about this sunrise probability? Well, it's solved exactly the same way. Laplace modeled sunrise as a probabilistic process, which has a probability theta tomorrow of rising or 1 minus theta of not rising. You just have to agree on how many days of sunrise have we seen. You can take the humanistic perspective, you can take the scientific perspective, or you can take my undergraduate perspective, which Shuvendu will share with me, which is we never saw the sunrise. But in either way, you can show that the posterior distribution is beta n plus 1, 1, and the expectation of posterior is n plus 1 divided by n plus 2. It's a application of the same idea, except that I observe that all my capital N binomial trials have capital N heads showing up. And then my question is, what's the probability of the coin that represents the chance of sun rising tomorrow? And this is how Laplace modeled it. And Laplace himself said this is not very reasonable. If you had a more mechanistic and a more scientific explanation of this process, you might get a much smaller probability of the sun not rising, or much larger probability of the sun rising. So with that, I will stop here. We'll take a break for 5 minutes. Hopefully you can get some questions in before the break. So we'll get 3 minutes of questions and then take the 5-minute break. When I come back from the break, I will talk about semantics of probabilistic programs.
Sriram, let's have a couple of questions. Okay. And then I would reintroduce you, since we had some hiccups on the live stream. Okay. So the questions are from Yuhao, who asks, do the soft constraint statements modify the distribution after executing the statements?
Absolutely.
And this might go back a few slides.
Yes. So I'm going to talk about the semantics of probabilistic programs, right? When I do that, you will observe that every path in the program has a probability that that path would have arisen. And then the soft constraints are going to depress the probability of that path. So think of it as a constraint, where another way of thinking of a soft constraint is something like this. So if I had a soft constraint on my path, right, I execute the program, I come to a soft constraint. So again, the soft constraint gives a probability, let's say 0.4, which means that the probability of proceeding is 0.4 somehow. Okay, but this is a different kind of probability. So in the Bayesian inference, you will see that this probability comes here. It's the probability of observing the data given the prior. Okay, so I will explain how the soft constraint comes in and somehow modifies the probability of proceeding further.
Okay, we have Marcel asking about slide 16.
Okay.
Aren't the left approach just the right one with MAP?
Sorry, the left approach is the right one with the?
Is the same as the right one with MAP. Maximum.
Okay. So, okay, now you're dragging me into something where I'm not an expert in. Okay, so statisticians debate a lot about Bayesian and frequentist. The left approach is a comedy of my understanding of how frequentist approaches work. But though I've talked to a frequentist and they took total exception to this, right? So, but roughly the left approach, you can think of it as giving a point value. And here the left approach doesn't have a prior. So the notion of a maximum a posteriori probability doesn't exist in this world because there is no prior. So if there is no prior, so people in this camp don't believe in the Bayesian approach, right? So to them, probabilities are essentially frequency, or the number of trials that show success divided by the total number of trials, right? So that's how you define probability going down to measure theory. So something like theta here, your belief should not have something like a probability. Having said that, there have been many intermediate steps where, so in this world, the closest thing you come to a map is you add something called a regularization. My spelling, forgive that. You have something called a regularization, which serves the same approach here as a prior. So you give different weightages to different parts of your hypothesis space. And here you would regularize and you would get a point estimate, which would roughly be the map. So there have been a lot of interpretations, a lot of procedures coming from here in this world have been interpreted in this world as the same procedure with a uniform prior. So there is a lot of back and forth where they come up with this very similar ideas, but they give it different interpretations. And as a non-statistician, I must say I am very confused. But yes, you are right. That's the short answer. A map would get you very close to here, except you wouldn't call it a map because that's not allowed in this world. You would call it something like a maximum likelihood under some regularization. Okay, that's my understanding. I could be wrong. Good statistician, if there exists one in the audience, could correct me and call me to task on this. Okay, maybe we take the 5-minute break now.
Thanks for the break. I think we're recharged and ready to go.
All right. Wanted to thank everyone for the great questions that are coming in on Slack. Please keep those questions coming. Personally, wanted to thank my student Alex Chakarov for fielding these questions in real time. Thank you, Alex. Where we left off, I wanted to talk about probabilistic programming semantics. The semantics of probabilistic programming gets a little bit tricky. I will be the first one to own that. Okay. Let me talk about it in two distinct cases. Let me talk about it for semantics, for probabilistic programs with purely discrete distributions. So you're allowed to flip coins, you're allowed to choose random variables. There are some discrete distributions over countable sets of states like Poisson distribution, where you're allowed to do those things, but you're not allowed to take a Gaussian random variable or a uniform random variable over an countably infinite set. So those are not allowed just yet. Under that situation, the semantics of a probabilistic program gets to be somewhat simpler to define. And what's the idea here? So let's take this example of a probabilistic program where you say, let me take a value P, which is a choice between 0.1, 0.2, 0.5, and 0.9. Let me flip 3 coins with probability P and record their values in x1, x2, and x3. If the flip turned up heads, they are going to be 1. Otherwise, they're going to be 0. And let me condition x1 plus x2 plus x3 to be equal to 2. And let me return the value of P as the return value of this entire program. Okay. Now imagine an execution of this program. So I start with the choice statement and I get P equals 0.1. And that happens. Now in this red box, I'm going to account for the probability of that happening. Now that's going to happen with this probability of 0.25. All right. Now I get to this next statement. I'm going to flip the coin and then get a 1 or a 0. Let's say I got a 0. What's the probability I get a 0 here? Well, it's the probability that this flip gave me a false. Well, it's 1 minus P then, because I flipped a coin with probability P. So it's 0.9, and I put that in a box. Likewise, I get x2 equals 1. That happens with probability 0.1. x3 equals 1. That happens with probability 0.1. And I get to this observe statement. And thankfully, x1 plus x2 plus x3 is equal to 2. 0 plus 1 plus 1 is 2. Therefore, I pass the observe statement. I'm allowed to proceed. The probability doesn't get modified because this is kind of a hard condition. It's either take it or leave it kind of condition. So the return value on this path is 0.1. The program returns 0.1. The probability for this path is 0.00225. Why is that? It's the product of 0.25 times 0.9 times 0.1 times 0.1. All right, let's take another example path. Here, x2 is 0, and that happens with probability 0.9. x3 is 1, that happens with probability 0.1. And this path, unfortunately, is not going to pass the observation because x1 plus x2 plus x3 is 1, which is not the same as 2. So you stop, proceed no further. The probability of this path doesn't quite matter for now. It will matter later on, but right now, we don't have to worry about it. This path is dead, as if it never, ever happened. Okay. Now, when you think about such a program and you think about all the possible paths, all the possible executions, it's discrete. So you have this kind of a tree. And you can imagine the leaves of this tree. And by the way, non-terminating executions of this program, in case you're wondering, will likely contribute to this red. I mean, you class all the non-terminating executions in red as well. Okay. With that semantics, you can say, let me collect all the values that have been returned by the program, along with their corresponding path probabilities. Okay. And so what happens is I get 0.1 here, and 0.1 in this path happens with 0.00225 probability. And I sum up all the successful path probabilities. When I sum up all the successful path probabilities, I get a denominator constant called K. Okay. And now the distribution that this program represents is this. 0.1 is returned. They add up all paths whose probability is 0.1 and divide it by the denominator capital K. And you would get, in this case, 0.0364. And that's the probability with which the program would return 0.1. 0.2 here is returned with probability, in this case, 0.008, 0.008. There should be one more path, which I haven't shown, with 0.008 probability. Divide that by the denominator K, which you have to get. Then you get the probability for 0.2. Likewise, you get the probability for 0.5. You get the probability for 0.9. And this is going to be the posterior probability that this program represents. All right. And that's the semantics of this program. It represents a distribution, if you will, and it has these 4 possibilities for the return values P and the corresponding probabilities. And remember, the probabilities are obtained because this observe statement blocks some of the paths and allows some other paths to execute. So some of the paths, the probabilities get redistributed between the paths that are allowed to go and complete execution. Good so far?
So I was expecting a question, Sriram, but I'm going to post that question because I'm curious. So okay. How is this measure defined for non-terminating programs and programs with unbounded number of paths?
Okay, so unbounded number of, I mean, this is just conceptual, right? So unbounded number of paths do not, I mean, because all your random variables are discrete, unbounded number of paths do not, you can ignore non-termination completely, right? Non-termination is the same as an observe failing. Such a path will never return a value, so it's never going to account for anything in the posterior. All right. Of course, you have to operationalize it and deal with non-termination in implementing this program, but let's just assume that never happens, or at least, you know, conceptually in the semantics, non-terminating paths are not going to contribute anything to the posterior. All right, that's number one. What was your other point here? So even if it's unbounded, right, it's still a discrete distribution. So you're going to get countably many possible values. And what you simply have to show is that, you know, those denominator constant is well defined. You don't get a divergence. You don't get like a divergent sum when you sum up the denominator, which it's not difficult to show, but it still requires some effort to show that. And I will show you some bad kind of programs where that may not happen. But in general, if K is convergent, then you can define these semantics by collecting all possible values that are returned by all possible executions of your program and dividing them by the relative probability. Does that answer your question?
Yeah, yeah.
All right. Okay. So ideally, you would want to do the same thing for continuous distribution. So let's take this continuous program with continuous distributions. Okay. I'm sampling from a Gaussian with mean 0, standard deviation 1. So this is a Gaussian centered at 0 with standard deviation 1, and call that mu, call that sigma as a sample from a uniform distribution between 0.1 and 5. Okay. Sample X as a Gaussian with mean mu, which is the sample here, and standard deviation sigma, which is a sample here. Observe that X itself is a Gaussian. This is a soft observation. Okay, so X itself is a Gaussian with mean 0.5, minus 0.5, and standard deviation 0.1, and return the pair mu sigma as the return value of this program. Okay, it's a continuous probability distribution. I would love to do the same thing. I would love to say, let me go take a path execution of this program. Let's talk about mu equals 0.2. What's the probability that mu equals 0.2? Well, unfortunately, the probability that mu equals 0.2 literally is 0. A probability of getting one particular value from a Gaussian distribution, which in theory can take uncountably many values, the probability of any given value is 0. So that's not an approach you can go, because then you get an uncountable sum of zeros. You get into all kinds of trouble, twist yourself into a pretzel that way, right? Not going to work. Another way you can do it is you can, instead of taking the probability, you can take the density function, if that makes any sense. But you have to be careful. It makes sense in a way, but you have to be really, really careful. And remember, when you do that with density functions, it's going to be a likelihood density. Let me talk briefly about this observe statement here. This observe statement observes a value x, a number x, under a Gaussian distribution. So as an example, in this execution, x was minus 0.1. So then you say, if I have a Gaussian centered at minus 0.5, what is the density function at minus 0.1 under this Gaussian? And that gives you a number like a density. And you can think of this density as somehow contributing to the probability density of this path. So now you have to think about probability densities of paths. You get into very tricky territory in measure theory. So this is going to be a very difficult problem to give semantics for all kinds of probabilistic programs with continuous distributions. And when they mix continuous and discrete, when you can flip coins and have continuous distributions, it's going to get ugly. All right. I'm going to show you a simple case when your program has finitely many control paths. So what's a control path in a program? Well, in this program, you see that there is only one control path. I take a value of mu, I take a sample for sigma, I take a sample for x, I observe, and I return. So it's a straight line program. Even though it's written in a functional program, I hope it's not a problem. So in this situation, you can write down a likelihood density for this program. You can say, what is the likelihood of returning mu and sigma? Well, the likelihood of returning mu and sigma is, first of all, what's the likelihood of sampling a value mu in this Gaussian? And that's this. What's the likelihood of sampling with some unknown constant k? I'm going to absorb all constants here because I don't want to write the 1 by square root 2 pi, blah, blah, blah. You can write a similar value for sigma. I'm showing it here because it's 1 divided by 4.9, though it should naturally be absorbed into this constant. What is the probability of sampling an x, this statement here, from mean mu standard deviation sigma? What is the probability of passing this observe? What's the likelihood of passing this observe? Well, you're taking x and you're sampling, regarding it as a sample from this distribution. So that gives you another here. And all constants gets absorbed in k. I am returning mu and sigma, which means x does not figure in the return value of the program. So I have to marginalize or integrate all x out. Okay, and this gives me a function called the likelihood function for this program. And as a function of mu and sigma, this is the likelihood of mu and sigma. Now, what I need to do is I need to get a denominator, which means I need to integrate this likelihood over all mu sigma. And that gives me a denominator. So let me call this denominator k hat. So then the posterior is 1 by k hat, the denominator times this likelihood. This is the semantics for a program with continuous distributions. You have to think of it as the product of density functions with integrals that integrate out all your observes. Of course, this only works for programs that are either straight line or programs that have finitely many paths. So in this example, related example, I have an if then else statement that's going to branch and give me 2 paths. So in this example, I can write something like this, and this is called the indicator function. In this indicator function, I say this is 1 if p greater than 0.6 or 0 otherwise. This is called an Iverson bracket. And I can go through this program somehow, and in a syntax directed fashion, I can translate this program into a likelihood on whatever it returns. I write a likelihood function and see these integrals here. There is a mu, there is an x, which don't figure in the return. I integrate them out. And then there is a denominator k, which is the integral of this likelihood that gives me the normalizing factor. And the entire program is 1 by k. LP is the posterior of the distribution p of this program. if it's well-defined. If these integrals are not well-defined, then this program is going to be problematic. It's not well-defined. If these integrals are well-defined, then it is okay. This gives you an idea of how continuous program semantics is going to work. It also gives you an idea of all the pitfalls and all the bad cases you are going to fall into when you have a continuous program. Okay, I will stop here and take questions.
We don't have any new questions, so we can keep going. A few more minutes.
All right. Okay, so I'm not going to go further into this. Let me just note down that not all probabilistic programs will make sense. Here's an example of a probabilistic program whose meaning is undefined under everything I've told you. So here I sample a Gaussian and I observe it to be 1 and I observe it to be 2. So its likelihood function of x is going to be this indicator function of x equals 1 and x equals 2 times a Gaussian distribution over x comma 1. And this is identically 0. So the likelihood is identically 0. So the posterior of this program is 1 by 0 times 0, which is not defined. This is a problematic program. No executions remain. And hopefully this answers Ganai's question on the Slack. Here is another program. Here you take a sample from a Gaussian and you say the sign of the sample is 1.0. Well, there are countably many executions that remain. The integral Lx dx is 0. But here, this is the likelihood function here. I needed to say that. This is not necessarily identically 0. It's just that I've taken some kind of infinite distribution and I've just sampled it at countably many points. The problem is the integrating the denominator, the constant is 0. So the meaning of this program is 1 by 0 times Lx, which is again problematic, not defined, not well defined. So, and trying to run or sample from these programs, most probabilistic programming systems will just die. All right. So I hope this is clear. And if there are no questions, I'm already running about 10 minutes later than I should have been here. I have 30 more slides. So I could
let's take quick questions that are there, and then maybe we can go fast.
Absolutely.
So Augustine asks, just to check, the semantics of continuous probabilistic program is a probability density function. I'm going to give the other question also. Mm-hmm. This is a clarification. Will there be a discussion on approximate inference methods, example, Monte Carlo? So.
Yes, very brief discussion. I will not have the time, but I will give you pointers on that. But let me answer the first question. The first question is, yes, it is a density function. So you have to be careful. Density functions generally will not exist for probability distributions. You have to be very, very careful. Density functions come from the derivative of the CDF. And if your CDF is not differentiable, you won't get a density function. So it gets you into a lot of very fine facts about measure theory and probability to convince yourself that density function exists. It makes sense. And therefore, you can have this probabilistic program be meaningful. As far as I know, there has been very little work on looking at checking whether a given probabilistic program is actually a meaningful program. I don't know that any tool actually does that. The tools that I work with do not just try to run the program. If you fail, crash out, do a division by 0, or you cannot collect samples, you will just throw up your hands and say you can't interpret this program. But whether a program makes any sense is, to me, almost an open question. There are some techniques that can solve it, but to me right now, I don't know too many works that actually take care of it. Okay, so far? All right, so let me go a little bit faster through some of the applications of probabilistic programs. Where do probabilistic programs come from? Well, they have come from a lot of sources. Traditionally, Bayesian networks, something called hierarchical Bayesian model. I already gave you an example of one right at the very beginning. From control theory, probabilistic programs come from this area called state estimation or filtering, which is super useful for people doing cyber physical systems. So all of these are good sources. Many of you should have seen our Bayesian network in your AI class if you took one of the traditional ones that we took. You introduce a Bayesian network, which is a probabilistic graphical model. Here it tells you that y1, y2, y3, y4 are random variables, and the probability of X is conditioned on y1, y2, y3, y4. It's not surprising that such Bayesian networks can be written out as probabilistic programs. There are something called hierarchical Bayesian models. I'm going to skip through these slides. I wanted to talk a little bit about this nice study in Oxford Review of Education, comparing test scores between different schools using a hierarchical Bayesian model. But I'm kind of out of time. I will go to the important parts of interest to me at least. So let me keep on with that. Another area is called state estimation. And state estimation is a very interesting area in probabilistic programming. Here, suppose you have a self-driving truck, and this is a picture of a self-driving truck that's driving on the road. It gets GPS readings, which are going to tell the truck where it is. And these are raw GPS readings. Now, the problem with these raw GPS readings is they are always going to be erroneous. And depending on the quality of GPS, depending on where it's driving, you get a small amount of error, and that puts your truck in the lane opposite to where it's supposed to be. And these happen all the time. So if the truck relies on raw GPS readings for its navigation, chances are it's going to have a collision with the divider line. It's going to steer itself out of the road, and the passengers are not going to be comfortably drinking their coffee, and so on. So one way to fix this is through what's called state estimation. So you think of these raw GPS readings as observations. So your goal is to estimate where the truck is, its position and velocity. And what happens is you can say that the truck has some dynamics. So the truck, let's say, is a Newtonian particle, so it moves in some way. If I know how I throttle the truck, how much acceleration I gave it, how I steered it, then there is a place where I expect my truck to be in the next step. So I expect my truck to be somewhere in the next step. But, and I can also say my GPS readings are observations. So I condition my expectation of where could the truck be with observations of the GPS reading with the GPS noise. So if I use that, then the posterior is going to give me an estimate of where my truck is. So typically in a Kalman filter, you would take the map estimate as where the truck should be at the next time step. And this idea is a way of smoothing out this kind of noisy observations to get a smooth extrapolation of where the truck could be using probabilistic programming. Most famous contribution here is by Kalman, who showed that if every distribution is Gaussian and the dynamics are linear, then this posterior is also going to be a Gaussian. And so Kalman showed how the posterior can be inferred very nicely through some kind of a recursive set of equations. And the nice thing is that the posterior at time t plus h becomes the prior for the next time. And that is a recursive application of probabilistic programming here for filtering. Okay. We use this in application to runtime monitoring of UAV trajectories. I will skip through a lot of this, just explain that we were interested in using probabilistic programming to in real time to figure out where could a UAV be over the next capital T seconds. And this is an important problem because UAV intrusions have become part of the news. So the idea here is if you know past measurements of positions of a UAV, the question is, can we write a probabilistic model that generates the future measurements conditioned on these past measurements, all right, using conditioning on these past measurements? Can we generate a distribution of future trajectories of this model and say that with some, at least with some probability, you avoid a collision? The trick here is to get it to be really, really fast in real time so that you can make predictions of even like 6 seconds ahead within like milliseconds. And if you're interested in how my students and I approach this problem, we have an upcoming paper. I'm really happy to share it with you. This would be how we would model it as a probabilistic program. Since I'm running out of time and there are very important topics to discuss, I'm going to skip it. We tried an experiment on this with 45 minutes of UAV flight, thanks to Professor Eric Frew, my colleague at Aerospace Engineering Department, and his students. And we were able to come up with posterior densities of where the UAV could be 6 minutes from now, and 6 seconds from now. Unfortunately, I don't have the time to discuss it further. I'm happy to, if you send me an email, I'm happy to send you a copy of the paper when it's fine. Okay, that was really fast. I'm sorry about that. Any questions so far?
I think we can keep going.
Okay, I'll keep going. So let me give you talk a little bit about what kind of probabilistic programming languages exist, what exists there already. And this is a huge space of languages. And this slide is credit to Frank Wood from UBC, who has a lot of discussion on this. So you can see that they come from 4 distinct communities: statistics, ML, AI, and PL. And Frank has kind of separated them. And I borrowed this slide from Frank, so I'll work with his classification. I would say the most widely used probabilistic programming languages are Stan, WinBugs, and Bugs. You might have even heard of WinBugs and Bugs, and a more recent version called JAGS, which is open source. These have been designed specifically for hierarchical Bayesian models, like the one I started this entire tutorial with. They link up very nicely with R and Python, which are very widely used languages in these communities. They have been widely used in psychology, biology, medicine, geology, astronomy. These are used in these papers where they present models, they condition it on data, present the results. Okay, so that's one example. Another example, very famous one, very widely used one, is called Infer.net from Microsoft Research. This uses a different approach. It tries to compile a C program into a graphical model, and uses a combination of something called variational inference. I'll mention what variational inference is in a few slides, and message passing to solve the inference problem. One of the big successes was this thing called TrueSkill, which is used in Xbox, was designed using probabilistic programming technology. Other examples are embedded domain-specific languages. So these languages are actually languages where you take OCaml or JavaScript or C or C++, you add sample and observe, and you use something like multi-threading, a combination of meta-programming with continuation passing style to implement inference algorithms on top of this program. Something like a backtracking search is implemented to do inference. I should mention Anglican, which is a very highly supported programming language, by Frank Wood, and it embeds into Clojure, which is a Lisp inside JVM. Another very nice language is called WebPeople, which is a JavaScript embedding. And these are very interesting probabilistic programming languages coming from the machine learning community. All right. Sorry, let me move on. There are logic programming languages that implement a declarative style. This Prism is not the Prism that we all know and love. It's a different logic programming language for probabilistic programming. There are languages like Psi and Hakaru. Psi came out in a CAV paper in 2016, which is a very nice paper that talks about how to write down the distribution of a probabilistic program that uses continuous and discrete variables, and how to use tools to simplify the integration that you have to do. And in many cases, they showed that you can do surprising amount of simplification to do inference. And Hakaru is another very interesting probabilistic programming language that also supports what's called exact inference. I wanted to talk about Pyro, which is a domain-specific language in Python, which has connections to PyTorch. It uses PyTorch for optimization. Edward is a probabilistic programming language for TensorFlow, so it does Bayesian machine learning inside TensorFlow. All right, so last but not least, there are many probabilistic programming languages that use higher order languages, unbounded recursion, unbounded for loops. And these probabilistic programming languages model things like distributions over functions, things like branching process models, and so on. Okay, so there is a use case for probabilistic programming languages that have unbounded recursion or unbounded for loops. I didn't want to make a big tour of programming languages because it gets tedious. I just wanted to show you how this works. Let me also briefly mention inference. Inference is a topic that's super important. There are lots of algorithms for inference. I mentioned 3 styles of inference: exact inference, sampling-based inference, and finding point estimates. I will talk briefly about exact inference and sampling-based inference just to give you pointers. This is not going to be a tutorial on inference. All right. With that being said, I already showed you this slide and I showed you that you can have these three kinds of inferences. How does exact inference work? Well, I would highly recommend this nice paper by Gare et al., I think Martin Vechev and Sasha Mikhailovich were co-authors on this paper, if my memory serves me right, in CAV 2016. It's a very nice paper where they literally take a program like this, but their programming language is imperative. In any case, they generate automatically this function from the program. And then they use a lot of rules, simplification rules to simplify this inference. And so that it can be solved in a closed form so that these integrations can be done. And you get a closed form expression for L sub P. You are able to symbolically calculate K. And on the face of it, this seems like a very, very hard thing to do. But one of the nice things they showed is you can do it for a surprisingly interesting collection of programs, which is super nice to see. So if you are interested in learning more about how this is done, you have to look closer into Psi and how they did it. I have to mention Hakaru as another language coming from Indiana University, which is another interesting project along the same lines, where they try and do exact inference. They connect to Maple and they try to use Maple and Haskell to simplify these expressions and solve these integrals. All right, so this can be done, but this is not the dominant way to do inference. The dominant way to do inference is sampling-based inference. So in sampling-based inference, you literally try to interpret the program by sampling from these distributions and somehow use a kind of backtracking search to deal with the observed statements. And such a procedure gives you all these samples. So you run this program and you ask for, let's say, 100,000 samples, and it gives you these 100,000 samples. And if you ask for capital N samples, where n goes to infinity, they have a theoretical convergence property. In the limit, they show that for any function, any well-behaved function you're interested in, if you compute the average of the function over the samples, that converges to the true expectation in the posterior of that function. So this should be f of x. All right. And this is called convergence in law or convergence in distribution. Now, I could spend hours and hours talking about these Monte Carlo methods, and they are called sequential. There is a wide variety of them. There are two important classes, something called sequential Monte Carlo methods, something called Markov chain Monte Carlo methods, but it's going to get really, really long. And by the way, if you're interested, there is something called the PPAML Summer School, where Frank Wood and others have done an excellent job of explaining some of these Monte Carlo methods. And those should be the people explaining Monte Carlo methods. But, you know, let me give you a cartoon slide on how these kinds of methods work. Examples, like two very popular ones, are called particle filters and something called Metropolis Hastings. Okay, so in a particle filter, what you do is you take n different threads or n different copies of the program and you run them in some kind of parallel lockstep. So anytime the programs hit a sample statement, you sample according to the distribution using a random number generator. But anytime you hit an observe statement, you stop and you look at the probabilities that are generated by these observe statements. If it's a hard observe statements, you kill the execution. If it's a soft observe statement, you have these numbers, these probabilities that come from these soft observe statements. These are called the scores. What you then do is you resample to keep your number of executions, these are called particles, to be the same, but you resample in proportion to the score. So if S1 is large, then you generate lots of copies of this particular state that corresponds to S1. If S3 is small, you generate one copy. If for some states, if it's too small, you generate no copies. This is called resampling. After resampling, you reset all the scores to 1 and you continue this execution. This is called a sequential importance resampling. To implement it, you have to multi-thread your program and have parallel executions, or you do some other trick, take over your interpreter and execute lots of copies of your program in parallel. Another interesting idea is called Markov chain Monte Carlo method, something called Metropolis Hastings, where if you have one execution of your program, you try and propose, you change this execution to a new execution. And one way you could do it is backtrack to some point in this execution, draw different samples and try to run a new set of samples. And you compare the old probability with the new probability. And you have a rule for accepting the sample or rejecting the sample. Okay, so this is all high level, but there are other places which explain these kinds of methods, these kinds of inference methods further. But note that you have to either have multiple copies of your program executing in parallel, or you have to have this ability to backtrack to some point in the program, re-execute with different samples and see whether you want the new execution or the old execution. And this is how you would generate lots and lots of samples, which converge in law to the final distribution. Okay, so this was really rapid, but are there any questions that I can answer in a couple of minutes?
There was only one discussion around Prism in the Slack channel, but I think we could take it later.
Yeah, so it's not the same Prism, it's not the same probabilistic programming, sorry, it's not the same verification tool Prism, it's a different Prism. I can post a link in the Slack channel later. Another class of inference algorithms to briefly mention is called variational inference. There is a huge review by Bley et al. Called Variational Inference, a review for statisticians that I found to be interestingly very readable. And so here the idea is your posterior is a very complicated unknown distribution. What you want to do is approximate this from a nice family, and this family could be a Gaussian or some family with parameter mu, and find a member of this family which minimizes something called a Kullback-Leibler divergence. It's a way of measuring distance between distributions. So this is a distance between distributions, between the member of the family and the actual posterior. How you do this is you have to use an optimization engine like TensorFlow or PyTorch or some kind of an optimization engine that does gradient descent on this mu to find the minimizer, and that minimizes the Kullback-Leibler distance. The problem with this kind of approach is it's non-convex and converges to a local minima. There are no guarantees in practice. The nice thing is it's extremely fast for really large probabilistic programs over very high dimensional state spaces. It gets you an approximate answer rather fast. Okay. I wanted to mention some work in the verification programming languages community on how you can optimize, because inference is one thing, but you can actually rewrite your program or change the way you execute your program to make inference faster. And one way to do it is if you have hard conditioning, you can try and compute preconditions and move the condition statement closer to the sample statements. Because if you did that, then you don't have to do the intervening computation to find out whether you're going to die or live. You're going to find out whether you're going to die or live much earlier. So Aditya Nori had a really nice paper with Sriram Rajamani and others in a system called R2, where they show how you can use symbolic execution to make this kind of movement nicer. There's a recent work by Peter Katoon and his students as well, along similar lines. Another idea is probabilistic program slicing, removing operations that are not necessary so that your inference and your queries can be answered fast. Now, obviously, you can see that slicing is tricky, because if you wanted to take a traditional program slicer and slice this program, you would happily remove these two statements. But if you remove these two statements, you're going to completely change the meaning of probabilistic program. So probabilistic program slicing is very tricky. There is some papers by Aditya Nori again, part of the R2 project, and some work by Anindya Banerjee that comes to mind. There are other papers as well. You can look at that. There's a lot of work on incremental computation where you can try to avoid recomputing unnecessary computations to make some probabilistic inference algorithms fast, all right? And I can give you the full form references. I'll post the full form references if you're interested. Okay, any questions so far?
Let me redo the questions. There are a couple of questions related to this.
Okay.
So I'm not going to expand the acronyms. For MH, HMC, and VI, you need derivatives.
Yes.
which is hard if you want to observe predicates. Could you comment and explain? This
Yes.
is from
So,
Sebastian, and let me read the second question
Mhm.
from Hari, who says, do the Monte Carlo Markov chain inference techniques work for programs with continuous distributions?
Okay, let me answer both questions. So you're right. Metropolis Hastings, Hamilton, Monte Carlo, variational inference need your program to be differentiable. So if you have hard conditions, you cannot do that. One way to is you can make your conditions soft. You can take your and your hard conditions into soft conditions. There's a standard way you would do it in machine learning using sigmoid functions, for example, and try to do it that way. I don't know that anyone has done this. Most of the languages that support HMC, VI, but by the way, MH doesn't need derivatives. Pure Metropolis Hastings doesn't need derivative. But if you have these kinds of procedures that need you to take the derivative, well, you need to have a program that's differentiable. If it's not differentiable, you have to give up. And so automatic differentiation is a well-researched area. So people do a lot of that in these areas. And then programs that are not differentiable, they just throw up their hands and say, you can't do that. That's how the systems that I know work. And the second question was, do these algorithms work on continuous distributions? They actually do. You have to work with likelihoods. And the problem is, of course, are you interpreting the right semantics of the program? You can prove that in case-by-case basis, you can prove you are interpreting the right semantics, but it's not a given. Okay. So that part, I think, is very, very important, that for continuous programs, the semantics can be tricky. And sometimes you get these Metropolis Hastings or your particle filters will throw out your program and say, this program makes no sense to me, but it might actually be a correct probabilistic program with well-defined semantics. And I've seen that happen. I can give you examples of that. Okay, but they do work on continuous distributions as well. All right, let me move on to verification, which is a very, very important topic for probabilistic programs. I will motivate some major approaches to verifications quickly. So what kind of verifications do you want to do? Well, you want to do the standard verification. You want to do assertion verification. You want to verify assertions about probabilistic programs. You want to do quantitative verifications, prove bounds on probabilities and expectations of programs. You want to think about termination of probabilistic programs, especially when you have unbounded loops and recursion. You want to think about uncertainty propagation. How do uncertainties in the program affect the final result? And all of these problems have been solved in the verification community. I wanted to point out a few important motivations. For example, Albert Guthi and others talked about something called verifying fairness of probabilistic programs. So here, if you look at a probabilistic program, let's say that processes loan applications, and let's say it takes a lot of inputs about the user, and let's say one of the inputs was race. And they tried to prove that if you change the race of the user without changing anything else, the probability that the user is given a loan is always within 1 minus epsilon, for a small epsilon, of the original probability. In other words, the sensitivity of the program to race as a variable is small, is provably small. Okay, and so they had this nice paper where they showed an application of how you turn that into a verification problem and you solve the verification problem. Another major area where verification of probabilistic program is useful is in differential privacy. Here, you want to ask questions like, if you have a database that's telling me how many prescriptions of a drug X are there in Boulder, Colorado, and it says 23. And then you say, how many prescriptions are there for people younger than 95, and it says 21. Well, then you know that there are 2 people who are 95 or more years old who are being prescribed this drug X. And what happens if there are just 2 people who are older than 95 years in Boulder? Well, then you have violated someone's privacy in this manner. So Cynthia Dwork and others have this idea called differential privacy, where they add randomization to do query answering. They have these mechanisms for enforcing privacy. And probabilistic programming, a lot of work has been done, especially by Gilles Barth, Anupam Datta, and many others, on proving correctness of these differential privacy mechanisms, which just turn out to be verifying properties of probabilistic programs. Another example is uncertainty propagation. If you have these kinds of systems that do repetitive tasks, you want to ask what's the probability that they are able to successfully complete these tasks. And that's an example of verifying some assertion is true at the end of a probabilistic program, or finding out the probability of this assertion. There are a lot of techniques for verifying probabilistic programs. I won't talk about Prism, which is a very, very important tool for verifying properties of finite state, timed, and even some infinite state probabilistic programs. They don't have conditioning, but they have non-determinism and they have assertions as well. Statistical model checking is another very important area which deserves a tutorial of its own. There's been a lot of approaches using symbolic execution, core logic extensions, some martingale-based approaches based on something called concentration of measure inequalities. I am running out of time, unfortunately, so I'm going to jump through some of these approaches quickly for the lack of time. Symbolic execution, you can imagine how you can execute different paths in the program. And there has been a lot of work on tying symbolic execution with something called model counting or volume estimation. Okay, I've just posted references. There is a lot of references that you can look at. There is a very nice work on Hoare style reasoning or Dijkstra style reasoning using what are called pre-expectations by McIver and Morgan. This is a very, very nice book by McIver and Morgan, which explains how to do this on finite state probabilistic programs. I recommend this book as very nice reading. There's been a lot of work by Frederick Gretz and Louis-Peter Tatun on mechanizing this and automatic invariant inference. There's been a lot of work by my student Alex Chakarov and myself on tying this to something called martingale theory and using that to extend this a little bit to infinite state probabilistic programs with continuous distributions. Unfortunately, I will skip all of this good stuff. There's been work on termination. Krishnendu Chatterjee and his students have a really nice book chapter and survey on probabilistic programming termination, talking about all the work that's been done in the last 4 or 5 years. Again, it goes back to something called martingale theory, using something called super martingales as ranking functions or the analog of ranking functions to prove termination. Okay, so there is a lot of work there, and I really do not have the time to go through all of that. So finally, let me get through the end of this talk where I wanted to talk about how can we contribute to probabilistic programming. Well, we can contribute in 2 ways. One is contribute as users, another is as contributors. So as users, we want to talk about data-driven. How do we do data-driven formal modeling, data-driven specification inference, data-driven testing, data-driven verification, where we incorporate data into how we do our standard verification tasks and do it in a precise, in a meaningful manner that builds confidence in the kind of systems we are verifying. We can do it as contributors. We can do it as contributors to make probabilistic programming even greater. So let me briefly mention data-driven model induction. So you can do probabilistic programming to think about models as being guided by model parameters. And you can say what values of model parameters makes the model fit some observation data. And in regular machine learning, you would get one value of these parameters, which is the most likely one, or the map value. In probabilistic programming, you get an inference and you get a distribution of these parameters, which means that you get a distribution of different models that predict the same data with different likelihoods. And you can think about what this means for verification. This means that in verification, you can consider lots and lots and lots of hypotheses and look at under what hypothesis is my property verified, under what hypothesis does my property fail. And you can talk about some kind of reliability notion. You can talk about uncertainty. So this gives a very promising approach that's much more exhaustive for verification. Let me talk about another idea, which is testing. So in this, probabilistic programming ideas are very good at generating inputs to systems. As an example, Hussam Abbas, Rahul Magaram, and others looked at generative models of human heart EKG signals, and they use the generative model to generate lots of EKG signals that can test a pacemaker implementation. Another example, which is much more recent, is Dan Fremont and Sanjit Sesha's work on something called Scenic, which is a probabilistic programming language with conditioning and constraints, where they generate road, pedestrian, vehicle images for testing object detection in convolutional neural networks in self-driving cars. And here, the generative model generates lots and lots of test cases for us to test a system, which is really nice because it gives us a systematic way of writing test cases that are somehow probabilistic and adding constraints. You can think about data-driven specification. A lot of work has gone into finding out temporal logic formulas from signals. Most of it comes up with one temporal logic formula, but you can induce it with multiple temporal logic formulas. There's a lot of work to be done on non-determinism, or what's called imprecise distributions. So a lot of this talks about precise distributions with well-known mean, well-known variance, well-known distribution functions. You can change that. And there's a work on how to do it with non-determinism to specify distributions where the mean and the variance can be non-deterministic. You can also turn it around and do posterior inference on imprecise probability models as well. Okay, so I wanted to mention some further sources. I don't want to mention them one by one, but there is a lot of really good sources on learning a lot of the underlying theory and the underlying methods which we use in defining probabilistic program for Bayesian inference, for probabilistic, for simulation-based methods, understanding probability theory itself, which is like the operating system around which the whole thing is built. A very nice book on verifying properties of probabilistic programs, which is very well written and very understandable. It does a host-style reasoning, Dijkstra-style reasoning. I like this book by Dubashi and Panconessi on martingales and martingale theory. And then here is a nice book on probabilistic programming, which describes a language called Figaro by Avi Pfeffer. And there are some nice surveys that are coming up. Sorry about running out of time. I have a few minutes for more questions, but I wanted to thank some of my colleagues for really helping me with this talk, and National Science Foundation for keeping me funded from 2013 to research this area and think about verification problems in this area. Thank you so much.
Let's give Sriram a round of applause. We still have many questions. I'm going to read some of the questions. So there was a question about PRISM going back a few slides. So this was from Sebastian Chungus.
Okay.
Isn't the PRISM language for probabilistic verification we all use and love an instance of probabilistic programming language, although being much like assembly? So let me just read the other question so that you have all the questions. Raul Pardo asks, has it been studied what inference method to use based on program? I assume that different inference methods work differently depending on the program.
Yes, okay. Okay, let me start with the PRISM question. I think PRISM is a probabilistic programming system. You can easily implement hard conditioning. And I dare say it will probably work a lot better than some other hand tune, because if you're going to use symbolic representation of states, if you're going to use, there's going to be a paper on IC3 for MDPs by Peter Petun. I'm looking forward to that paper in a few days. All those ideas can be used for probabilistic programming. So if you want to turn around and make PRISM a probabilistic programming system, I believe it can be done. Though I think Martha or someone who works on PRISM should answer that question better than me. But I thought about this and I think it can be done. And I think it will be faster for some of the problems we are interested in solving. But I don't know if it will implement soft conditioning. Definitely hard conditioning, some form of probabilistic programming with discrete. I can immediately see that happening.
So there was a second question about
second question, yes, it's a very, very nice question. You are absolutely right. There is a little bit of, you have to know, looking at some probabilistic programs, what inference methods to use. I can give you an example. So if you look at most of the probabilistic programs I wrote, let me take an example. I generate the sample that I'm interested in at the very first statement, and that's what I'm returning at the very last statement of this program. So it turns out that if you're going to do this, certain kinds of inference procedures are going to suffer, like particle filters by themselves will not be so good because you generated a value of P up front, and then you're running through the program without being able to change the value of P. So there are some very, very nice relationships between the sort of program you write and the inference procedure that you would use. Anglican claims to have a library of inference procedures that mixes a lot of kinds of inference procedures, and you should be, I mean, ideally you would try a lot of these inference procedures and see which one works best. That's one way to do it. The other way to do it would be to think about writing a paper on matching probabilistic programming languages with the kind of inference procedures that would work best with them. I already gave you an example which would fare poorly under something like a particle filter. So something to think about, and maybe a paper coming up in next year's CAV.
I think we exhausted all the questions. Great discussion. So I have one question, and I mean, I know we're out of time. I mean, you mentioned this idea about having a family of specifications instead of one specification, temporal specification. As a user, how do I make sense? How do I use that to my benefit?
So imagine a situation. Okay, so let's imagine a situation where instead of you interested in, you're given some data. Okay, so you're given some data. This is not the slide. You're given some data, and you want to know the top 10 possible specifications. Okay, this is not map inference, because map inference gives you the most maximum a priori, maximum a posteriori estimate. So it gives you one specification. Maybe you want 10 different explanations, right? A probabilistic programming system could help you get to 10, like a top 10, right? So that's an example where you would want multiple specifications as explanation. Another way is, suppose you want to, you have different specifications, S1 and some probability, S2 and some probability. So maybe you can come up with like, check your system under S1, check your system under S2, and look at all the tests that your system pass and give a reliability score on how likely is it that your system is going to satisfy some specification, right? So there are ways in which there are natural problems in data-driven world where this idea of exhaustively, or at least semi-exhaustively, generating all possible hypotheses with some probability attached to them and then checking them might be useful, right?
Makes sense. Thank you. I don't see any more questions, so I guess we can end the session. Thank you, Sriram, for this wonderful tutorial.
Yeah, thank you, everyone. I'm going to be answering questions on Slack throughout this program for CAV, and I'll post the material online through my webpage at some point, and probably have Shuvendu send a note or post a note on Slack where the slides are posted.
Well, thank you, everybody, for tuning in. Bye-bye.
Bye. Thanks, everyone. Thanks, Shuvendu.
Thanks, Sriram.
So
sorry for the glitch. Yeah.
So I should stop the live stream now?
Yes, please.
Okay. And then end the meeting?
Yeah, Sriram, do you have anything else to?
Nope, I am done. Thank you so much.
Let's have the Slack channel and iterate on the Slack channel. Thanks to Alexander Shakarov, who was channeling in for you.
No, Alex, it was very nice of him to do that. Thank you, Alex.
Thanks to him. Bye. Thanks,
Bye.
Brandon.
Okay.
Appreciate
Sure.
it. Bye.
Bye.